Hi everyone, so we're going to introduce the concept of energy. Hopefully we've had a discussion on the importance of energy in the history of our society and even how it's still very, very relevant today. So in this first of tutorials, we're going to introduce the simplest of energies, the energy of motion, kinetic energy. We're going to define it, we're going to derive an equation, how to calculate it, and then look at a simple problem. A follow-up tutorial will look at the other types of energy, namely potential energies and even thermal energy. So if we go to define energy, what exactly it is, it's really hard to do. So we're not going to define what it is. I'm just going to put an IDK. We don't know. It's not made up of material. It has no mass. It has no volume. But we know it's real. We've proved that it's real because we can see how it transfers in many different forms throughout systems when we do work on it. So perhaps the best way to look at energy is not what it is, but what it does. And what we can say it does is it does work for us. And so that's why we spend so much of our energy, pun intended, looking for energy sources, either to run our machines or to stay alive, for energy to do the things that we need to do. Because when we have energy, we can do things, work, we can move things, we can, whatever it may involve. So it is perhaps the most essential aspect of any science is energy. So I'm going to start off with an example going back to the egg drop lab. Okay? And I want to look at how we could use a concept of energy if we had known about it at the time to help us maybe to design our landing pad. So let's say based on how far the egg falls. Remember, the egg is dropped from the ceiling and it's going to hit the ground and it's going to fall a certain distance. Well, we can calculate the amount of energy it had based on the distance it falls. We haven't learned how to do that yet, but let's say it has 1.7 joules of energy. And we know that we don't want the egg to feel any more than 30 newtons of force, so we can ask ourselves, what minimum distance, in other words, when I put a landing pad there, what distance does this have to be such that when it stops the egg, it doesn't give it more than 30 newtons? And what we can say is, well, we know that the energy, when it hits the pad, the energy does work on the pad. Okay, so the type of energy, you don't need to know it here, but it's kinetic energy, goes to work. And that work is equal to the force the egg felt multiplied by the distance over which the egg falls. So based on the energy, which we get from the velocity, if that's 1.7 joules, and F can't be greater than 30 newtons, if I solve for D, right, that's just simply going to be 1.7 divided by 30. So let me punch that out on a calculator. We see that's 0.057 meters, which is 5.7 centimeters. So what that tells us is our landing pad has to be at least that thick or tall in order to stop the egg in a great enough distance to minimize the force. And if we had known that, then we could say, well, we can't use a landing pad or a foam, even if it's the softest foam on the planet, that is thinner than that. Okay, so let's look at work to energy. There's a number of ways that you can get, there are different types of energy you can get based on a work, depending on the situation. So let's take the simplest situation, which is case one. There are no opposing forces. In other words, I exert a force on an object and there's nothing opposing me. There's no gravity, there's no friction, etc. What happens is, then your work goes towards kinetic energy, as we've mentioned. And what is kinetic energy? It's the energy of motion. Okay, so the abbreviation used for kinetic energy is KE. So if I do 10 joules of work on an object and there's no other forces except for my applied force, then when it leaves my hand or leaves the machine, whatever I'm using, it will have that amount of energy. And it will be in a form of motion. So when something's moving as kinetic energy, we'd like to be able to calculate that kinetic energy based on its motion, namely its mass and velocity. So we're going to take the idea of work to kinetic energy and derive an equation right here that tells us how to express kinetic energy in terms of the motion. It's a derivation you don't have to know, but I'd like to show you anyway. So we can start with the idea of work, which is a force times a distance. Now in terms of motion, force is equivalent to ma, so this becomes ma times d. And I'm going to put the parentheses here for a reason. Okay? So F is ma, that's the second law of motion, d is d. Now why did they put the parentheses around a and d? Because if you recall from kinematics, there's an equation that says your final velocity squared equals your initial velocity squared plus 2 times a times d. So let's assume, just for ease problem, that our initial velocity is 0. So if I solve for AD, we see that A times D is equal to VF squared divided by 2. So if I put that into here, I see that the work done, which is equal to the kinetic energy, is equal to 1/2 mv squared. I'll get rid of the final velocity. Okay, so that's our equation for kinetic energy. It's 1/2 of the mass times the square of the velocity. And that squared part is really important because doubling the velocity gives you a lot more energy, whereas doubling the mass gives you just more energy. Another way we can calculate it is change in kinetic energy, which is final minus initial. So based on this equation, that is 1/2 the mass. And the reason I'm pointing this out, because very often the mistake students will do is they'll do final minus initial and square it. You can't do that. It's got to be final squared minus initial squared. And if you're thinking they look like the same thing, they are not. So just be careful. All right, let's just finish up with an example problem. So I've got a car with a certain mass moving with a certain initial speed and experiences a force. So we press the gas pedal even more of 3,000 newtons, and we do it for 100 meters. So we can answer a bunch of questions of what did the car start with and how is it going to change. So first question, what's the car's initial kinetic energy? Okay, that's pretty straightforward. Ke is 1/2 mv squared. So we've got 1/2 of 1,000 times, and don't forget to square the velocity. Okay, so I think I can do this in my head. This is 400,000. Half of that is 200,000. So I'm going to put in 200 kilojoules, 200,000 joules of energy. Okay, that's just a convenient way of writing it. Next question. So by the way, what does it mean that it has 200,000 kilojoules? Well, if that car were to get in an accident, it was to slam into something, then it would give up all that energy to the other thing that hit itself and even its surroundings. And so it's going to go towards damage, especially, excuse me, in terms of thermal energy, sound, etc. So the more kinetic energy you have, the more damage you can do. But in terms of the car's motion, kinetic energy isn't the main focus. It's how fast it's going. All right, now we did work on it by pressing down on the gas pedal. So how much work was done on a car during the boost? Well, work is a force times distance. So you're told it felt a net force of 3,000 newtons. So we're taking into account drag. We're subtracting it. It's just built in there for 100 meters. And so that's 3,000 times 100, 300,000. So that's 300 kilojoules. I'll keep it in terms of kilojoules. So what is the new kinetic? What was the change in kinetic energy? Sorry, not the new one. Well, the work equals, let me take that back. The change in kinetic energy can be thought of as a change in velocity squared and all that, but it's also equal to the work. That's why we calculated the work here. So that's simply going to be 300,000 kilojoules. I want to emphasize that you can calculate kinetic energy or changes by looking at work. It's not always just going to be 1/2 mv squared. So now I can ask, what's the final kinetic energy? Well, it's simple. The final kinetic energy, which I'll call Ke prime, is equal to the initial plus whatever change we had. So we start off with 200 kilo. We added 300 by the extra work we did, so now we have 500 kilojoules. So how fast is the car now going? We can take this, and now that we know kinetic energy, we can set it equal to 1/2 mv squared. So whereas in this problem we use V to find Ke, now we're going to use Ke to find V. So I'm going to solve algebraically because I think it's good for you to see this. So if I solve for V, I move the 2 over to here, I multiply both sides by 2, divide by m, and then take the square root. So it's the square root of twice my kinetic energy divided by my mass. So let me punch that out on the calculator. And you can certainly do that. 2 times, don't forget to put in the 500,000. Don't put in 500. Oops. Divided by 1,000. And then don't forget to take the square root. And you get 31 about, I'm just rounding, meters per second. Okay? So it turns out we could have figured this out using the second law of motion. We could have figured out the car's acceleration is F over m, and then use the acceleration to get a final velocity. We're going to see that this method, while it maybe not look easier than what we were used to, it turns out it will be a lot easier when we extend this to other forms of energy and conservation of energy. Okay, next question. If distance was doubled, how would the change in kinetic energy doubled? So if we're going to do a proportions here, we want to find an equation for kinetic energy based on distance. So we're not going to use 1/2 mv squared because it doesn't have distance in it. Well, if you paid attention to one of the earlier problems, that's equal to the work done during the interval, and that's force times distance. So we see that Ke is directly proportional to distance, so it's going to be twice. sketch relationship between KE and V. So if I put KE here and V here, what's the graph going to look like? Well, we should understand that as V goes up, KE is going to go up. The question is it going to be linear or not? Well, that's why we use an equation. So of course, the equation we're going to use is 1/2 mv squared. And we see that KE is proportional to V squared. So that squared means it's not going to be a line. We're going to get a parabola. So doubling twice the V leads to 4 times the kinetic energy. So if you're in a parking lot moving a certain speed and you bump into something, you will do a certain amount of damage. If you're going twice as fast, you're going to do 4 times the amount of damage. So kinetic energy grows very quickly with speed. Okay, so I'm going to stop there. What we'll see in the next tutorial is we're going to look at other types of energy when there are forces that were being opposed. And then we'll put it all together for the grand finale in the conservation of energy.